Case study, Transforming Cybersecurity Defense, TechSecure's pioneering journey towards AI-enhanced intrusion detection systems. The cybersecurity landscape is undergoing a profound transformation, with AI-enhanced intrusion detection systems becoming indispensable for combating sophisticated cyber threats. At the forefront of this technological evolution is TechSecure, a company specializing in cybersecurity solutions for large enterprises. The company's Security Operations Center team, led by Chief Information Security Officer Laura Garcia, faces mounting pressure to bolster their defenses against increasingly complex cyber attacks. TechSecure's SOC team includes data scientists, network security analysts, and machine learning engineers who work collaboratively to enhance the company's IDS capabilities. The team is exploring several cutting-edge AI methodologies, including machine learning, deep learning, reinforcement learning, and ensemble techniques to improve their IDS framework. During a routine security audit, the team discovered that their traditional IDS struggled to detect zero-day attacks and polymorphic malware. Laura emphasized the urgency of integrating AI-enhanced IDS to effectively tackle these threats. The first step involved analyzing historical data to identify patterns of known attacks. Here, the team faced a critical question. How can machine learning algorithms help in creating a more adaptive and robust IDS? To address this, the team chose to implement supervised learning algorithms such as support vector machines and random forests. They trained these models using labeled datasets of known attacks and benign activities. These models were then continuously updated with new data to adapt to emerging threats. The result was a considerable improvement in the detection of new attack patterns that previously went unnoticed. At the same time, the team began experimenting with deep learning models like convolutional neural networks and recurrent neural networks. These models automatically extracted and learned features from raw network traffic data, enhancing the accuracy of detecting complex attack patterns. A pivotal question arose: what advantages do deep learning methods offer over traditional machine learning techniques in IDS? The deep learning-based IDS demonstrated superior performance, particularly in identifying denial of service and probing attacks with higher accuracy and lower false positive rates. This was a significant breakthrough, as it allowed the team to manage large volumes of data and uncover intricate relationships within the network traffic that traditional methods missed. However, the dynamic and ever-changing nature of cyber threats necessitated a more proactive approach. The SOC team explored the potential of reinforcement learning to not only detect intrusions, but also respond to them effectively. They posed a critical question: how can reinforcement learning be utilized to enhance both detection and response mechanisms in IDS? By implementing reinforcement learning algorithms, the IDS learned optimal policies for detecting and mitigating attacks by interacting with the network environment and receiving feedback through rewards or penalties. This enabled the system to prioritize critical alerts and allocate resources efficiently, significantly reducing response times to high-risk threats. The team also recognized the value of ensemble learning techniques, which combine multiple models to improve overall detection performance. They integrated methods such as bagging and boosting to reduce false positives and false negatives. An important question emerged: how do ensemble learning techniques contribute to the robustness and reliability of IDS? By aggregating the predictions from multiple base models, such as decision trees and neural networks, the ensemble approach provided complementary strengths. This led to enhanced detection accuracy and resilience against adversarial attacks and evasion techniques. The robustness of the IDS was significantly improved, making it more reliable in various threat scenarios. Despite these advancements, the team faced challenges related to data availability and quality. How can semi-supervised and unsupervised learning techniques be employed to overcome the limitations of labeled data in IDS? To address this, the team employed semi-supervised learning techniques that leveraged both labeled and unlabeled data. This approach improved model performance by utilizing the vast amount of unlabeled data available in their network traffic. Additionally, the deployment of AI-enhanced IDS required considerable computational resources. Leveraging cloud computing and edge computing technologies provided scalable and cost-effective solutions for deploying AI models. One of the criticisms of AI-enhanced IDS is the black box nature of many machine learning algorithms, which can obscure the decision-making process. The team explored the concept of explainable AI to enhance transparency and trust. They confronted a crucial question: how can explainable AI be integrated into IDS to improve model interpretability and trust? By utilizing techniques such as feature importance analysis and model visualization, the team provided insights into how the AI models made their predictions. This enabled security analysts to verify and validate the results, making it easier to identify potential biases and errors. The transparency offered by XAI enhanced the credibility and acceptance of AI-enhanced IDS among users and stakeholders. Threat intelligence integration was another significant focus area. How can threat intelligence feeds be incorporated into AI-enhanced IDS to improve detection capabilities? Incorporating real-time threat intelligence feeds into IDS allowed the AI models to recognize and respond to specific threat patterns more effectively. This enhanced the system's ability to detect advanced persistent threats and zero-day exploits that were previously undetectable using traditional methods. The integration of threat intelligence provided contextual information about known threats, enriching the AI models with actionable insights. The collaborative nature of cybersecurity defense cannot be overstated. The team explored collaborative and federated learning approaches to enhance collective security. They questioned, what are the benefits of federated learning in the context of AI-enhanced IDS? Federated learning allowed multiple institutions to train AI models on their local data while sharing only model updates rather than raw data. This preserved privacy and confidentiality, leading to more robust and generalized models that could detect a broader range of threats across different environments. Collaborative learning facilitated knowledge sharing and improved the overall security posture of participating organizations. In conclusion, the integration of AI into IDS has revolutionized the field of cybersecurity, offering advanced solutions to detect and mitigate sophisticated cyber threats. The case of TechSecure's SOC team exemplifies how machine learning, deep learning, reinforcement learning, ensemble techniques, and collaborative approaches can be harnessed to enhance IDS capabilities. The challenges of data availability, computational requirements, and model interpretability were effectively addressed through innovative solutions, setting a new standard for adaptive, accurate, and proactive cybersecurity defense mechanisms. The exploration of threat intelligence and federated learning further underscored the importance of collaboration and contextual awareness in modern IDS.